Okay. Welcome back, lads and ladies, to the wonderful world of Calc 1 Honors. We're in an interesting place today because we have 2 student teaching days coming up, and I have to hold back just a little bit what I would normally do today to let them do their thing. And that's okay, that's not a problem, but it does mean that we have kind of a little less to do today than we would normally have to do on a given day. Grab some more paper and we can start talking. I need to check and see exactly where we left off last time. Just to make sure we haven't missed anything in 5.2. I think we were talking about properties of the definite interval. And we discussed the properties related to kind of splitting up the interval, right, from A to C and then from C to B. We discussed the properties to do with even and odd functions. And we discussed properties to do with flipping the bounds, spitting out a negative, those things that come from the Riemann sums. Sorry, I'll let my cat out real quick. I would like to get us a little bit more practice with those properties. And I think there are 1 or 2 other things that we should say, even if they're sort of natural consequences. Yes, Talia, we definitely do need to meet. Let's see, for some reason, maybe I misscheduled the thing in Zoom. I didn't see it on my schedule, and that would be my fault if I did miss our meeting. Yes, we definitely do need to talk. We should talk over the weekend then. Let's see. Scheduled to turn the end of class. Yeah, I do remember talking about that with you now. I don't know why it wasn't showing up on my schedule, but I kind of operate mechanically like that. If the thing isn't there, then it just I have too much to keep in my head. So that does sound like it was my fault. Like I put something in the wrong place, probably wrote the wrong date. Let's do that over the weekend then, because you said today you'd only be able to come for like 15 minutes of the office hour. Is that right?
Yeah, I can't really come to office hours today, because I have to go to like other appointments and stuff like that. But this weekend I'm free.
Okay. Yeah, let's plan a time for the weekend then. What works for you?
Probably like anytime after like 3 p.m.
After 3? All right, let's do Saturday at 3:30.
Okay, yeah, that sounds good.
All right.
Thank you.
Put it in here, make sure I get the date right. It must have been what I messed up because I didn't get my notification. 30 p.m. We'll plan to do a 1-hour meeting. Have you been preparing? I don't want to burn too much class on talking about this, but have you been preparing the material? Are you familiar with the antiderivative stuff, or is this something that we've just sort of started?
Yeah, I've started learning it. I need to go over a few more concepts, but I think I know how I want to teach it and stuff like that.
Okay, I'm going to send you a new Zoom link here, and before I forget, I'm going to put this in my phone so I get on this alarm. Okay, there's no one messing up. We definitely do need to talk. 40 p.m. Saturday. Yeah, okay, so for 1 day, 4 hours and good. All right, then I will see you tomorrow at 3:30. We'll go over the format and the content and make sure everything goes nice and smooth on Monday.
Okay, thank you.
I'd like to summarize today. Let's see. I'm going to talk about more properties of the definite integral. And this is still section 5.2. So some of those properties have really nice geometric interpretations, like the even odd function thing and the splitting up the interval thing. Some of those geometric interpretations are very clear in certain cases and less clear in other cases. Like we saw the even function thing made a lot of intuitive sense if you think of the function as always being positive. But if the function is sometimes negative, it can be a little bit not obvious how that results in the doubling of the integral from 0 to a. The same is true for that property where you split up the integral from a to b as integral a to c plus integral c to b. The way I drew the picture there, the number c was between a and b, but it turns out you can do that shit even if c is outside the interval a to b. So I want to look at some examples like that where the application of those properties is not as intuitive as the geometry in the original picture suggests. And then I also want to look at some consequences of those properties, some of which are things that I would say we could deduce, but maybe we don't want to. You know, if there's something that you use a lot, you don't want to have to cook it up from first principles every time you go to play with it. So continuity, integrability, evaluating integrals. We've done plenty of this. Sums. We've done plenty of this. We can do a little more practice with those if we want. Evaluating integrals as areas is fun. Midpoint rules I'm not going to make you do. But here are the properties that I'd like to summarize. So let's do it. Your book writes them in a certain order. I'm going to change that order around to express what I think are the most important. So first, linearity, by far the most important. So the integral of a sum of two functions is the sum of the integrals. And the other piece that, together with this, tells us the integral is a linear operator is that if k is a constant, then the integral of k times f of x dx is k times the integral from a to b of f of x dx. So these two are the properties we will use more than anything else. Then there's the one we proved by thinking about how delta x in the Riemann sum changes for the integral from a to b compared to the integral from b to a. If you flip the bounds over, right, the limits of integration, if you swap them, like integral 0 to 1 of some function, is the negative of the integral from 1 to 0 of that function. Normally, we think of the lower limit as being the smaller of the two numbers, but that's not always the case. And this can be used to rearrange an integral so that that is the case. Like if somebody hands you the integral from 5 to 2, you can flip the 5 and the 2, putting the 2, the smaller guy on the bottom, just knowing that when you flip those, a negative will pop up. We had also integral a to b f of x dx is equal to the integral from a to c f of x dx plus the integral from c to b f of x dx. And I quietly implied, when I showed you this fourth property last time, I quietly implied that c is a number between a and b. Turns out you can do this no matter what. Right? C doesn't necessarily need to come from between a and b. C could come from elsewhere. So if you had the integral from 0 to 1, I could do that as the integral from 0 to 3 plus the integral from 3 to 1. It's a weird thing to do. And more often we use it going from expressions like this down to an expression like this in combination with number 3. But I just want to emphasize that C need not lie between A and B. And that's not at all intuitive. I think it's the result is quite intuitive if C does lie between A and B, because then you can think of it as kind of splitting up the area into 2 areas. But it also works if C is outside the interval AB. There's one other thing
Why
here.
is C need not lie between A and B, so C can outside of A and B?
Yeah. Yep. It's strange, but I will try to explain to you how this is a true statement, even if C isn't between A and B. The trick is, if C lives outside the interval AB, then you can split the integral up, and one of the pieces that comes from splitting that up will cancel. I'll show you. Before that, though, there's 1 or 2 other properties that your book does write down here that I wouldn't consider properties necessarily. More just consequences of the definition, but that's what a property is, and your book calls it a property. So let's say also we have the following facts. Following useful facts.
The screen is covered by
Yeah,
the file thing.
Gotcha. Zoom pops that up when it finishes converting the video. So one of those useful facts is that if you integrate a function from A to A, the integral from A to A of f of x dx, this is always going to be 0. Because there's no width, right? Think of the integral as an area. It's the area under f from A to B, or here, from the lower limit to the upper limit. If you're not giving me any width, then you can't have any area. Another one, the integral from A to B of a constant. Think about the graph of a constant. It's a horizontal line. So the integral from A to B is the area underneath that horizontal line from A to B. That's the area of a rectangle whose height is k and whose width is b minus a. So this would be k times b minus a. There's a little picture that comes with this guy. I'll draw it for you. So here's your constant function k. Your x-axis, your y-axis. If a is right here and b is right here, then this area is the area of a rectangle whose height is k and whose width is b minus a. Later, we'll be able to see these as consequences of other theorems, but for now, it's just useful fact. And then we also have the result on even and odd functions, which I'm not going to write down again, but certainly are things that you should know. I'm sure you have them in your notes from last time. But these are the properties that we use most often, especially linearity.
Is that a C or an A at the very bottom?
At the very bottom, this is an A.
On the left side.
A is everywhere. I don't think I have any C's. Yes.
Okay.
The only C shows up in this guy.
Also, why is f of x times d of x, why is that equal to 0?
It's not that f of x times d of x is equal to 0.
Yeah.
It's that the integral from a to a of f of x is 0.
Oh, okay, I got you. Thank you.
Yeah, the reason for that, the picture here, is that if you have some curve f, and you're integrating from a to a, that's the area under that curve from A to A. Well, there's no area there. So this guy, let me annotate in blue. This is the area of a rectangle. The base is, this width is B minus A, and the height is K. Here, this would be the area under a single point. The width is equal to 0. So the area is equal to 0, right? A single point doesn't have any width at all. So we can't have any area. Area is a two-dimensional measure.
Thank you. Yeah, I misread the bottom letter for B.
Oh, no worries. Yeah, no worries at all. All right. So other stuff we want to do, I want to convince you that property 4 holds even if C is not between A and B. I'm going to fiddle with this for a minute to try and show you that. Let me make sure I'm not missing anything else that your textbook discusses here. I don't think we are. Yeah, no. Oh, yeah, we do need to talk about these comparison properties also. That's right. Okay. I knew there's something else. Okay. So first, let me convince you that 4 is true. Even if we're, so why is 4 true? Even if C is not between A and B. Question. So I have some curve here. Maybe A and B are here. And maybe I'll drop C over here. The area in here this would be the integral from A to B, right? And what I claim is that this should be equal to integral from A to C, f of x dx, plus the integral from C to B, f of x dx, even with C all the way over here. So the integral from A to C would be all of this area under the curve, right? We'll shade in pencil. So the integral from A to C, this guy, is the pencil shaded area. What is the integral from C to B?
Minus from B to C.
Very good. So this is integral A to C, f of x dx, minus the integral from B to C, f of x dx. Well, the integral from B to C is exactly this, right? So if I take the total pencil shaded area and I subtract this, maybe I'll shade that purple. What we're saying here is that the blue is equal to the pencil minus the purple. And that does make sense. All right, what is this blue? Well, I could think of it as all the pencil shaded area minus the purple shaded area. So even if the number c is way outside the interval a to b, the integral from a to b, which is the blue shaded area, is equal to the integral from a to c plus the integral from c to b. You can split this up over some number that's not even in the middle, because this guy, if c is to the right of b, then this lower bound is actually bigger than this upper bound. So the natural thing to do is to flip it over. And by property, what was it, property 3? Yeah. This is from here to here. This is by item 3. And now here, what we're saying is that the blue area is equal to the total pencil area minus the purple area. And this is evidently true, which is true just from thinking about the areas. And I always thought that was pretty cool. This is the source of some very confusing problems if you don't understand why it works. So I really wanted to show you why this works, even when C is not between A and B. Really quick, let me take a peek at a problem we can solve using this that is maybe more interesting. Let's see. 8 to 10. Yeah. So let me look at example 7. If the integral from 0 to 10 of f of x is 17, and the integral from 0 to 8 of f of x dx is 12, can we find the integral from 8 to 10? So it's not as straightforward as the problem we looked at last time, where you just add this and this, because integral 0 to 10 plus integral 0 to 8 is not the integral from 8 to 10. But what I can do is try to think of the integral from 8 to 10 as a difference of two integrals. More than one way to approach this. So one solution is to say, okay, well, the integral from 0 to 10 of f of x dx is equal to the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx. And this is maybe the more straightforward way to do it, but it requires thinking a little bit ahead. So this is going all the way from 0 to 10, and the piece I'm looking for is just from 8 to 10. So I elect to split this at 8. And then I can plug in the pieces that I know here. 17 is the value of this integral. 12 is the value of this integral. And the integral from 8 to 10 of f of x dx is what I want. So 17 equals 12 plus the thing I want, subtracting 12 over. 17 minus 12 is 5. Another way of doing this which appeals, kind of starts with the thing you want and appeals using, appeals to property 3 using the way we were just describing it. You could say that the integral from 8 to 10 of f of x dx is weirdly the integral from 8 to 0 of f of x dx plus the integral from 0 to 10 of f of x dx. So again, I'm using property 3. The first solution makes sense if you think about things geometrically. If you're just trying to like grindy approach this problem though, using property 3, saying I want to start with the thing they told me to find and somehow apply properties of integrals to get the answer, you can say, I'm going to do something fucking weird. I'm going to split this integral up at 0, even though 0 is not between 8 and 10. This is still a true statement. So what we're doing here is using c equals 0 in property 3. And then I can rearrange these. So the integral from 8 to 0 is the negative of the integral from 0 to 8. And the integral from 0 to 10 is the integral from 0 to 10. And now I can just plug in the integral from 0 to 8, I was told is 12. So this is negative 12 plus the integral from 0 to 10, I was told is 17. And negative 12 plus 17 is still 5. So two different ways of thinking about the problem. One requires a little bit of forethought, right? Where we kind of ask ourselves, well, what's the biggest area I'm looking at here? What's the integral that has the largest a to b? And then I split that up in a very natural fashion at 8. And one of those pieces turns out to be the thing I want. But this does require thinking ahead a little bit. On the other hand, if you want to just start by writing down the thing we're trying to find, you can get to the result by splitting it up at 0, even though 0 is not between 10 and 8. Pretty nifty, right? Slightly counterintuitive, but it works. Okay. The last thing we need to talk about in this section.
I have a question.
Yes.
For the 0 to 8 and the 8 to 0, their result is different. One is positive, the other is negative, right?
Right.
But how about the number? Is it the number is same too?
So what we're saying here is that this piece is 12. So this negative is this negative, and this thing is 12. Is that getting at what you're asking? I'm not sure I'm answering the question you're asking.
If 8 to 0 f of x dx is it 12?
No, it would be this thing on its own is negative 12. Because it's the negative of the integral from 0 to 8.
Integral from 0 to 8 is 12.
Positive.
And the positive 12, but from the 8 to 0 is the other number is not equal to 12.
Correct. This piece on its own would be negative 12. because it's the negative of the integral from 0 to 8. So we can annotate a little bit here. Since the integral from 0 to 8 of f of x dx is equal to positive 12, integral 8 to 0 f of x dx is negative integral 0 to 8 f of x dx is negative 12. So if we just wanted to find this on its own, this would be negative 12. Is that feeling comfortable?
A little.
It's a little funny, right? So when you see an integral where the bounds are kind of in the wrong order, where the larger number is down here and the smaller number is up here, this has to do with something called orientation. How do we describe orientation without being able to talk in higher dimensions?
Based on the way that it's facing?
Right. So let me show you something here. I think probably easier than that. Well, yeah, okay. So every, how do I say this? I need pictures for this. These pictures are more complicated than they need to be. Here, let me turn off the screen share. Let me just show you here. All right. I'm just going to grab something I have handy. This cube, this Rubik's Cube, has an orientation. It has an inside and an outside. So if I want to, I could always say what direction is pointing outside the cube, right? That is called an orientable manifold. A line has orientation. You can go from here to here or from here to here. We might call this the forward orientation. We might call this the backward orientation. When we're thinking about integrals, they also have an orientation. So when you integrate from A to B, we're talking about an oriented measure. You're measuring the area as you go from left to right. If you change the orientation to go from right to left instead, then that's going to flip the sign of the integral. It really is coming from that delta x piece. Remember that delta x, which we normally think of as the width of our little rectangles, it's more than that. Delta x isn't just a width. Width doesn't care whether you're going left to right or right to left. Delta x is an oriented measure of the line segment that you're integrating over. So when we integrate from A to B, we're not just talking about areas, we're talking about signed area, which means oriented area. So we're measuring the area as you go from left to right. And if you do that going from right to left instead, each one of those little delta x's becomes negative, which makes the whole thing negative. So the concept of a signed area is really not the right word. It should be oriented area. In Calc 3, you're going to learn how to find volumes of solids. And one of the ways to do that is by doing a certain integral with respect to a vector that points out from that solid. If you do that same integral with the vector pointing into the solid rather than out from the solid, you'll get the negative of that volume instead. This is actually a really big deal in the field of differential geometry. And let me just. Yeah, everybody loves these non-orientable manifolds, like the Klein bottle and the Mobius strip. But for example, this guy, the torus, is orientable. I can talk in a very real and clear way about the inside and outside of this donut. You can imagine a little arrow sitting here on the torus pointing out. And no matter where you move that arrow, its butt is like glued to the torus. No matter where you move that thing along the torus, that arrow would always point out if you started with it pointing out. And if you started with it pointing in, that arrow would always point in. So what we're really talking about when we say this property 4 here, what we're saying, or property 3, sorry. Ooh, I mislabeled this, sorry. So this is C equals 0 in property 4. Property 4 here. What we're saying isn't so much like the area is negative. We're saying that the orientation has been reversed, right? It's like your velocity going forwards or backwards. We always talk about just going in the forwards direction or going in the backwards direction, but the street outside doesn't have an arrow that says this way is forwards and this way is backwards. We're assigning an orientation. So what we do when we flip A and B is we flip the orientation. We're measuring, instead of going left to right, going right to left. And since on the x-axis, right, in the 2D plane, on your x-axis, the x values increase as you go to the right and decrease as you go to the left. When you flip the orientation and walk the other way, the signed, or better, oriented area changes sign, becomes negative. It's a little weird. I acknowledge that freely. It's not the most intuitive thing, because we like to think of these things as areas. Area has some physical meaning to us. I can talk about the area of this paper, but in truth, these are mathematical objects from differential geometry. And what's really going on when you flip the bounds, you're swapping the orientation. So I don't know if that helps things or makes things worse. You're asking a good question, and the correct answer is in here, if you want to read about it. There are some surfaces that are not orientable. For example, the Mobius strip is a famous example of a surface that's not orientable. If you take a Mobius strip and try to do that thing with the arrow, as you rotate around, the arrow will go from pointing in to pointing out. After you go around the strip once, you'll come back to that same spot, but the arrow will be pointing the other way. And that's what we mean by non-orientable. So an orientable surface versus a non-orientable surface is a tricky concept that kind of illustrates the question you're asking. Because the real line, thankfully, is orientable. We can talk about orientation swapping, which is what happens when we swap integral a to b into integral b to a.
So if interval a to b is not equal to the interval b to a, it's the opposite way.
Correct. Yep.
Okay.
Yeah, and the way I like to think about it is that normally I sort of measure this area in chunks moving from left to right. So I kind of think of what this integral does is it starts here at A, and it starts to pull a cover or a sheet over this region, and it's going from left to right. It's going in the positive direction. So once we get over here, we will have all of this area, and we will have measured it going in the positive direction. On the other hand, the integral b to a, it's working with that same geometric thing, that same region, but it's trying to start over here at B and carry that sheet from right to left. So the area is being measured in an oriented fashion. But this is all stuff way beyond what you need to know for this class. So for us, we should really just think of this as a property that comes from the Riemann sum. When you change A to B into B to A, the delta x in the Riemann sum becomes negative. So we say this integral is the negative of the original. And that's the simplest way to think about it. But there are deeper things here going on with the geometry. All right. Speaking of deeper things going on with geometry, analysts, not like actuaries or data analysts, but analysts in the mathematical world, people who do big boy calculus, their whole lives revolve around inequalities. Turns out approximation is sort of the whole game. We don't really get exact results very often, and when we do get exact results, it's because we look at limiting cases of approximations. This is true for everything in calculus. One of the most important things to be able to approximate is an integral. Obviously, we've seen plenty of that with Riemann sums. But what about using mins and maxes? If f is continuous, then by the extreme value theorem, f must attain an absolute min and an absolute max on the closed bounded interval AB. And we can use that min and that max to give a very rough estimate of the integral from A to B. So let me call that absolute min, the output, the y value there, little m, and let me call the absolute max big M. Okay, so let me draw a graph, a nice continuous function. And let's take the interval from A to B to be something like this. And I will pencil shade here the exact area bounded by F. Okay. So the pencil shaded area, I think we all agree, is the integral from A to B of f of x, right? F of x dx. Here, the absolute min is attained right there, and the absolute max is coming from one of the endpoints up here. So this would be capital M. And this would be little m. Everybody with me so far? I'm going to draw a rectangle with my mouse here. Everybody sees that the pencil shaded area fits inside this rectangle, right? Because that function, it never gets larger than capital M on the interval A to B, the whole pencil shaded area necessarily fits inside this rectangle. And no matter how I drew this function, this would be true. Wherever that absolute max is, if I draw a rectangle with that height, the whole pencil shaded region would fit inside. And similarly, this little rectangle fits inside the pencil shaded area. It's the opposite inclusion. And no matter how I drew that function, if I take this guy to be determined by the height at the absolute min, then that rectangle would always fit inside the pencil shaded area. In other words, let me do this in purple. this purple rectangle is always guaranteed to be smaller than the pencil shaded area. And this blue rectangle will always contain the pencil shaded area. What that provides for us is an inequality. So the pencil shaded area is the integral from a to b of f of x dx. The purple shaded area is what? Well, it's a rectangle, so it's this width times this height. It's little m times b minus a. And the blue shaded area, that's big M times b minus a. So this leads us to a theorem. If little m is the absolute min and big M is the absolute max for the function f on the interval, closed bounded interval AB, then little m times b minus a is always less than or equal to the integral from a to b of f of x dx, which itself is always less than or equal to big M times b minus a. Of the three areas, the purple is the smallest, the pencil is in the middle, and the blue is the largest. And there's no escaping that fact. This is sort of the crudest way to estimate an integral, right? Of course, we can do much better with Riemann sums or trapezoidal sums or anything like that. But sometimes this is good enough to get what you need. And it's an important thing to be comfortable with. I would like to work an example problem here. Let me grab one out of your book. I'll illustrate the other properties in just a second. Let me, yeah. So estimate the integral 0 to 1 e to the negative x squared. I'll give you just a second to get everything down.
Just clarifying, the one in the middle of the inequality, that's an a at the bottom of it, yeah?
Yeah. Yep.
Okay.
The integral from a to b.
Thanks.
All right. So use the theorem to give upper and lower bounds on integral 0 to 1 e to the negative x squared dx. So this integral e to the negative x squared turns out to be incredibly hard. by the way. Hugely important in statistics and probability. If anybody's ever taken a statistics class, you may recognize this as the normal distribution or bell curve. If you haven't seen this graph, now is the time to see it. Here it is. Now this is the bell curve where the standard deviation is 1 and the mean is 0, but of course you can shift it around. If I do that, then I can drag the curve left and right. And if I divide by the standard deviation, I can stretch the curve. So, nope, sorry, not all of that over S, just the exponent is to be divided by S. There we go, stretch the curve, whoop, like that. Okay, so this curve, hugely important in statistics and probability, describes things that are controlled by Bernoulli processes. Classic example is IQ. Whether you believe in IQ or not is a totally separate thing. I do not, pretty much bogus. But integrals like this, very, very hard to evaluate. So we want to estimate them. To do this, I need to find the absolute min and max for the function f of x equals e to the negative x squared on the interval 0, 1. And to find those, I use my closed interval method. So I'm going to compute f primed. That would come from the chain rule. So it's e to the negative x squared all primed. My inner function there is the negative x squared. So this would be e to some stuff, always differentiates to e to that stuff times the derivative of that stuff. That's the chain rule. And the derivative of negative x squared is negative 2x, and I'll write that out front. So it's negative 2x e to the negative x squared. E to some stuff, this is never going to be 0, right? Exponentials are always positive. The 2x piece will be 0 when x is 0. So critical numbers it's just x equals 0. Right? F primed is equal to 0 when x is 0, and it's never undefined. So according to my closed interval method, the absolute min and the absolute max must come from one of the critical number or the endpoints. The critical number is an endpoint. So we just have to compare f of 0 and f of 1. Well, f of 0 is e to the negative 0 squared, which is e to the 0, which is 1. F of 1 is e to the negative 1 squared, like this, which is e to the negative 1, or 1 over e. So little m, the absolute min, is 1 over e. And big M, the absolute max, is 1. Thus, by the theorem, little m times b minus a is less than or equal to integral a to b f of x dx is less than or equal to big M times b minus a. I just plug everything in here. Little m is 1 over e. A and B are 1, so this is 1 minus 0, less than or equal to integral 0 to 1 e to the negative x squared dx, less than or equal to big M is 1. So this is 1 times 1 minus 0. In other words, 1 over e is a lower bound, and 1 itself is an upper bound. Yeah, normal distributions appear to govern lots of things. It's interesting. Height is another example, right? If you within gender, because height is bimodal unless you split it by gender. But yeah, lots of things. So this would be my lower bound or lower estimate. And this would be my upper bound or estimate. And again, this is really rough, right? This is neither of these is very accurate. But we know that the actual value of that integral is somewhere between 1 over e and 1. All right. I really just have one more thing that I want to share with you guys, and that is a fact, and one more fact about definite integrals. Maybe before I move away, are there any questions on what we did here? Okay. There is a more general version of that theorem. And in words, this just says that definite integrals respect inequalities. Meaning, if f of x is less than or equal to g of x, then the integral from a to b of f of x dx will be less than or equal to the integral from a to b of g of x dx. And a special case of this says integrals of positive functions are positive, integrals of negative functions are negative. Your book says it like this. So if f is positive, then the integral of f is positive. If f is bigger than g, then the integral of f will be bigger than g. We do need to, yeah, I guess quantify this. We should say on AB. But in words, integrals respect inequalities. And the proof here is trivial. It's just a picture. I take a function like this, and I call this f. Take a function like this, and I call it g. Then the integral from a to b of f is just this area. And the integral from a to b of g is all of this area. Right? And clearly the blue area is bigger than the purple area, right? Because the purple area fits inside the blue area. So by inclusion, by inclusion, what I mean, one fits inside the other. The purple area can't possibly be larger than the blue area. But of course, the blue area is the integral from a to b of g of x dx. And the purple area is the integral from a to b of f of x dx. So smaller functions give smaller integrals. Larger functions give larger integrals. It's not as obvious if the functions are sometimes positive, sometimes negative, but again, it works just fine. Let me see if there are any sort of interesting problems for us to discuss. If not, then I'm going to wrap up the last bit of this lecture by trying to get you ready for some particular problems. Let me see, do we have anything like this in here? No. No. Okay, this is all pretty grindy. This is good stuff. But yeah, so instead of that, here we go. So this next bit is going to be a very gentle introduction to the fundamental theorems of calculus. All right, before I can show you the fundamental theorem of calculus in all its beautiful detail, we will need to learn about antiderivatives from Talia. After we have that, I will show you the full fundamental theorem of calculus. And then once we've done that, we will be learning about indefinite integrals from Dan. But to introduce this, I want to consider the integral from 0 to x of the function 2t dt. It might not be obvious right away, but this is actually a function of the variable x. You plug in a number for x and you get a number out. So if I wanted to compute f of 0, that would be the integral from 0 to 0 of 2t dt. And of course, that's 0, right? Integral from a to a is always going to be 0. F of 1 would be the integral from 0 to 1 of 2t dt. I'm going to draw the graph y equals 2t over here. This is the t-axis. Something like this, right? We'll work this as 1, 2, 3, 4. So if I want to do the integral from 0 to 1, we're talking about this area. And since we're on the graph y equals 2t, that height would be 2. So this would be 1/2 the base, which is 1, times the height, which is 2, 1/2, 1 times 1, which is 1. Sorry, 1/2, 1 times 2, which is 1. If I want to compute f of 2, that would be the integral from 0 to 2 of 2t dt. Should be the area of this triangle. And this height here is 4. Again, we're on the graph y equals 2t. You plug in t equals 2, you get 4 out. So this is 1/2 his base, which is 2, times his height, which is 4. That's 1/2 times 2 times 4, that's 4. If I want f of 3, that would be the integral from 0 to 3 of 2t dt. So that would be the area of this triangle. And the height there, this point right here is 3, 6. So that's 1/2 times his base, which is 3, times his height, which is 6, which is 1/2 times 3 times 6, or 3 times 3 is 9. And I'll do one more. If I were going to compute the integral all the way up to 4, capital F of 4.
How did you get from 0 to 1 2t dt is equal to 1/2 multiple 1 multiple 2 is equal to 1? How did you get that?
I'm thinking about this triangle. So the triangle that I've just kind of reshaded as purple here. This is the graph y equals 2t. And I want to integrate from 0 to 1. So that means I'm trying to find the area under the line y equals 2t from x equals 0 to x equals 1. So that's this triangle. And the area of a triangle is 1/2 base times height. So that's 1/2 this base, which is 1, times this height, which is 2. Feel okay?
But that is 2t. You put the 1 into the 2t is equal to, yes, that is 2t, but you have a 2 multiple t at there. So you plot the 1 multiple 2. I don't know how to get it.
So I'm just thinking of this, right? Just the integral from 0 to 1 of 2t dt. That's the area under the curve y equals 2t from t equals 0 to t equals 1, right?
Yes.
So what is that area? Well, that area would be this triangle. And the area of any triangle is 1/2 times the base times the height. So that's 1/2, the base is 1, right? And the height is 2, because when you plug 1 into f of t, or to 2t, you get 2 times 1, which is 2. So this point right here is 1, 2.
Okay, that's.
Feel better? All right, cool. So I'll compute f of 4. Yeah, Sarah's made a conjecture in the chat, and that conjecture is true. So the integral from 0 to 4 of 2t dt would be the area of the big black rectangle triangle here, which is 1/2 his base, which is 4, times his height, which would be 8. All right, this point up here would be 4, 8. And that's 16. So the pattern that you appear to see here, 0, 1, 4, 9, 16, that should jump out at you. 0, 1, 4, 9, 16. So it looks like, it starts to look like capital F of x would be x squared. Now here's the fun part. What is capital F prime of t? Well, if capital F of x is x squared, then capital F primed of x is 2x. So capital F primed of t would be 2t. And if you think you see a connection between this stuff, namely this thing, and this stuff, you are exactly right. The derivative of this thing is the same as the function inside, just that the variable changed. And that, my friend, is no coincidence. That is the fundamental theorem of calculus. Part 1. There's a part 2 also. And we'll discuss those in detail after we've learned about antiderivatives. So for now, what I want you to do is just continue working on the homework. Make sure you get very comfortable with the properties of the definite integral. If you do run into any trouble, you can come see me in office hours. I have an office hour this afternoon from 1 to 2 p.m., but I'm going to be on baby duty during that office hour, which means I'll have my son in my arms and can likely not do a whole lot of writing or typing, but I'm happy to talk. And as much as I can, I'll answer questions for you. I can maybe do a little bit of writing. But that is it for now. All right. Next time, we're going to learn about antiderivatives from Talia. Then I will teach you about the fundamental theorem of calculus. And then we will learn about indefinite integrals and the net change theorem from Daniel. I hope you guys have a good rest of your day. Please enjoy the weekend. And if you do have anything you'd like to talk to me about, come by office hours, shoot me an email or a Canvas message. Otherwise, I will see you all on Monday.
Will you post the
Thank you.
video today?
Yes, I will post the video today. Yep, I know
Thanks.
the video from Wednesday is not up yet, right? But I'll get both of those up right now. All right. Take care, gang.